Here is Justin Gilmer, who will speak on the density of happy numbers.
Thank you. Yeah, for those of you that don't know me, I'm a third-year PhD student. So we're going to consider this function on the integers, which sends an integer to the sum of the squares of its digits. And we'll be interested in the trajectories of integers when we iterate this process. So let's do an example. Start with 7, square it, we get 49. And then take 4 squared plus 9 squared, which will give us 97. And then continue 97 will go to 130. You have to trust me that the math is correct here. 130 goes to 9 plus 1, which is 10, which then goes to 1, which will go to 1, and then repeat. So 7 would be happy because it eventually reached 1. And so different examples, 6 takes a lot longer to repeat. So we'll see what happens. Continue, 17, 50, 25, 29, and keeps going. And then eventually we hit 89 again. So we hit 89 here, and then we eventually got back to it. So 6 would eventually hit this cycle starting at 89. And so 6 is not happy because it would never reach 1. And so because 7 hit 49, 97, 130, and 10, all those numbers are also happy because 7 hit 1, so all these are happy as well. And you can sort of modify, like 7, you can add a 0 to it, and you still will eventually get to 1. And you can also permute the digits. So 49, switch the 9 and the 4, you get 94. 94 should be happy as well. And so here's a fact. Every number eventually hits 1 or this cycle, starting at 4. And so sort of a sketch of the proof. Consider a 3-digit number. Then the largest, I guess, next number in the sequence for a 3-digit number would be the case where the number is all 9s. So, for example, 999 would be 243, which is 3 times 81. And any 3-digit number would have to be less than 243. And so it sort of follows that any number with at least 3 digits, the next step is less than what you started with. So a 4-digit number should be less than 4 times 81, which is certainly less than 10,000. And thus, any cycle has to contain an integer less than 1,000. So if you had a cycle where every number is bigger than 1,000, then we decreased at every step. And there's no way we got back to where we started. So does that make sense? Okay. So you then just perform a computer search and check the trajectories of all the integers less than 1,000. And you can find all possible cycles. Okay, so we can certainly generalize this. Why square the digits? We can also cube it. And so if we cube it, there are actually 9 possible cycles. We get a few fixed points. And then there's a cycle of length 3. This cycle. So it's not too important what the cycles are. It's kind of fun to just plug it in your computer, like try base 9 and then say sending a digit to like the 4th power, or pick any function. You could send 1, or you could send 2 to like 5, and then 3 to 10, and just randomly just choose what each digit goes to. Consider the cycles you go to. And you can ask, well, what percentage of numbers eventually arrive at a certain cycle? So not just 1, but what percentage of numbers when cubing do we get to 153? What percentage hit to 370? So I think I can answer any question of this type modulo computer computation. And hopefully I can convince most of you guys that I can do that by the end of this talk. Okay. So they, as far as I know, they were introduced to, I guess, serious mathematicians when this guy, Richard Guy, mentioned them in his book, Unsolved Problems in Number Theory. And he asked the following questions. He asked, do there exist arbitrarily long sequences of consecutive happy numbers? And he also asked, what can be said about the density? And there's a number of other questions you can ask, like the heights of happy numbers, like how long does it take to get to 1? So like say I want the minimum example of a number of height 10. So what's the smallest number that takes 10 iterations to get to 1? And a lot of these have been studied. As far as I know, no one's said anything about the density yet. I did a lot of searches and couldn't find anything. Okay, so the answer to the first question is yes. The first paper was in 2000, and they showed it for just the case base 10 and squaring the digits. And then this second group, Grunman and Teeple, generalized it. And the most general result is by this guy, Halpan, which is, he showed in 2008 that there are arbitrarily long sequences of consecutive EB happy numbers. So EB means we're in base B, and then the exponent is E. So the standard example is 10, comma 2, or sorry, 2, comma 10, base 10 and exponent 2. And he gave this sufficient condition that handles a lot of cases. And then today, I'm going to at least try to show that, sorry, this should be 0.18. So the upper density is at least 0.18, and the lower density is at most 0.12. Okay. Any questions so far?
For the upper density for what? For the case, the base 10 squaring them?
Yeah, so yeah, just for base 10 and squaring. And yeah, I said that my algorithm should answer for any case. I didn't bring the numbers with me, but yeah, like for cubing the digits, it was something like 10% as well would go to 1 eventually.
So why these particular ones? If you work harder, can you lower the upper density and raise? Can you narrow the gap?
Well, so this, so the gap is already like the asymptotic density can't exist because the upper density is strictly larger.
So is it sharp? We don't know how sharp it is.
Right. So the upper density could be larger, and I have no way of bounding the upper density from above. But it's pretty satisfactory in that we know that we can't say anything about the asymptotic density. That limit does not exist. Okay. All right, so for those, just to define what upper density mean, if you haven't seen it, let Fn count the number of integers in a set S that are less than or equal to n. The upper density is just the limit supremum of the density, and the lower density is the limit infimum. Okay, so here are the happy numbers less than 1,000. All I'm trying to show with this is just that permuting the digits doesn't change anything. So for example, we have 964 here. Permuting the digits, 946 is also happy. And adding zeros doesn't change anything. I mentioned that before. And it's pretty random. I don't think anyone's been able to give a nice, clear, concise statement of when a number is happy. And it's related to the partitions of an integer. So for example, 44 is happy, and we can partition 44 as 2 squared plus 2 squared plus 6 squared. That means that the number 226 should be happy as well. And in fact, again, permuting the digits shouldn't change it. Okay, so you look on Sloan. Here are the densities less than different powers of 10. So less than 10, there are 30% of those numbers are happy. So in particular, 1, 7, and 10. Less than 100 is about 20%. And Sloan went up to about 10 to the 20th. And it's about 14% all the way up there. So, and in a second, I'll mention how to calculate these densities for much larger powers of 10. Okay, so I'm going to define p sub n comma I to be the number of n-digit integers whose image is I. So for example, p sub 2 comma 25, this is how many 2-digit numbers hit 25. And so 5 hits 25, 50 hits 25, 34 and 43 do as well. So p sub 2 comma 25 is 4. And so say, for example, we know the distribution of all 3-digit numbers. So just say I know p sub 3 comma I for all I. And I'm saying that I can use this to calculate p sub 4 comma I for all I. So let's write all 4-digit numbers as the union of these intervals. So I'm collecting all numbers whose first digit, I guess, is 0, then all numbers, 4-digit numbers whose first digit is 1, and then digit 2 up to 9. And say, for example, we're trying to find how many 4-digit numbers hit 107. Then p sub 4 comma 107 is given by this recurrence relation. So the number of 4-digit numbers that hit 107, well, it's the number of numbers in the interval 1 to 199 that hit 107. That's just p sub 3 comma 107. And then it's then the number of numbers between 1,000 and 2,000 which hit 107. That's just p sub 3 comma 106. Because when you take the image of these numbers, that 1 is always there. Like the image of this second interval is the first interval, but shifted by a factor of 1. Is that clear? Okay. And then, yeah, so this recurrence relation follows. Is that clear, everyone? Okay. And if you do it by computer, we'll get p sub 4 comma 107 is 90. So 90 4-digit integers hit 107. And in general, this recurrence relation is true. So this gives us a pretty fast algorithm to compute the density of happy numbers less than 10 to some power. So to do that, you first use the recurrence to calculate p sub ni for I from 1 to 81 times n. I don't have to go farther because the maximum image of an n-digit number is just when it's all 9s. That's when it's 81 times n. And then find by brute force just the happy numbers in an interval 1 to 81n. And then I'm going to output just the sum over all those happy numbers in that interval p sub ni. So if I count how many n-digit numbers hit 1, plus how many n-digit numbers hit 7, plus just continue for all happy numbers in this interval. All right. So this algorithm is actually pretty fast. So here's the density up to 10 to the 7,000. So what this graph means is, so say this point here is 6,000. This means the percentage of numbers less than 10 to the 6,000 is whatever this is. So that's about 14%. And just something interesting to note, so there's a peak at about 10 to the 400. About 18.5% of those numbers are happy. And the upper density, when I say that I can show the upper density is at least 18%. That 18% comes from this peak here. And I'll explain, so the rest of this talk will be how to use that peak to sort of construct intervals with a lot of happy numbers in it.
So can you say, eventually, like starting at a certain place, what's the density? Like 10,000?
So, I mean, like what my result says is that when we measure by computer, say this peak at about 18.5, that has to keep happening forever.
Oh, eventually.
Yeah, eventually you have to go above 18.5 again. There's a little bit of loss. There's like a millionth of a percent loss, and then also this valley here at about 11.5, we actually have to always go below that eventually. All right, and so yeah, I should mention that this graph is actually I got from this guy's website, Sean Spiller. His code's a lot faster than my Maple code. My Maple code will only do about 10 to 300 before I have to start waiting an hour or so. And his he used the same idea, but he's just, he didn't use Maple, he used like C. And his is much faster. Like this took about 10 hours to generate. So, okay. So I want to study these P sub ni a little bit closer. So again, P sub ni is the number of n-digit numbers which hit I. And another way to write it is just the number of sequences of n terms where each term is in the set 0, 1, 4, up to 81, and such that this sequence sums to I. And this is exactly the number of integer compositions of I into n parts. So an integer composition of I is just an integer partition of I, but the order doesn't matter. And I forced that every part is taken to be in this set. And so these sort of questions are well studied, estimating the number of integer compositions. And so an example, 25 can be, here are the 4 compositions of 25 using elements of this set. All right, so it has a nice generating function. If you were to multiply out this polynomial and then ask, what's the coefficient in front of x to the I, you would get exactly P sub ni. And again, we only have to sum up to 81 times n because an n-digit number can't go past that. Any questions? All right. And I want to switch to a probabilistic viewpoint. So consider just taking a random n-digit integer x, and I want to call y sub n to be that corresponding random variable. And let's call x sub I to be the random variable for the ith digit. So the x sub I should be, it takes 0 with probability 10%, 1 with probability 10%, 2 with probability 10%, and so on. Then the image of y sub n is just going to be the sum of these h of x sub I. And that's because the image of an n-digit number is exactly, it's the sum of the squares of its digits. So, and each of the h of x sub I, these are all IID random variables. So this sum should approach a normal distribution. And I'm going to call the digit mean and digit variance just the mean and variance of h of x of I. So the mean is just the mean of one digit. And the variance, if you did it, would be about 24.2 squared. And this is really all I care about when I'm considering an arbitrary function. I really only care about what is the mean, the digit mean and digit variance, say when we're cubing the digits, or in base 100 and squaring the digits. What the digit mean and digit variance will tell me is how far out I have to go with my computer before I can actually say something specific about the density. And more on that later. And then, yeah, the mean and variance of h of yn, you just add these means and you add the variances. For independent random variables, the variances, for the sum of independent random variables, you just sum the variances. So, and again, central limit theorem says this approaches normal distribution. And the density of happy numbers in this interval is exactly the probability that this random variable is happy. Because if I take a random n-digit number, the probability that's happy is the number of, it's the number of integers which hit a happy number divided by all the integers. So, and I'll sort of use this interchangeably. Sometimes I'll talk about when I'm trying to find the density of happy numbers in some interval, I'm really trying to find the probability that this random variable is happy. Any questions so far? Okay. Okay, so here's a graph of h of yn compared with the normal distribution. The red line is, so the first graph is for the case n equals 10. So the red line shows the probability that, say, a 10-digit integer hits, say, like 300. So the probability that a 10-digit integer hits 300 is whatever this point is, about 0.005. And you can see, indeed, the normal distribution is, it's a decent approximation. For n is 100, the red line is much smoother, but still the normal distribution doesn't give it exactly. But we can learn a lot from this picture. Namely, say I want to know the density of 100-digit integers. So the density of the integers from 0 to 10 to 100 is exactly the probability that this red curve is a happy number. And so it really only depends on the happy numbers between 2,000 and 3,000. In fact, if I knew that about, say, 10% of these numbers were happy, you would sort of guess that about 10% of the numbers from 0 to 10 to 100 would be happy as well. And the general setup for the rest of this talk will be, I'll have some interval, say 1,000 to 6,000. Let's just pretend for a second that I know that 18% of those numbers are happy, but I don't know where they are. And what I'm going to try to do is, if I know that 18% of these numbers are happy, I want to choose n such that this bell curve moves along this interval. And I'm trying to find a choice of n that hits happy numbers with high probability. And if I know that 18% of these numbers are happy, you would sort of expect that at least some choice of n would hit happy numbers with about probability 18%. And because if all those bell curves missed happy numbers, then well, where were they? So it could be. The rest of this talk will make that sort of argument rigorous. Okay. So does everyone understand the general setup of what I'm going to try to make this averaging argument? If I'm averaging over all possible choices of this bell curve, I want to make this argument rigorous to say that if I know that there are at least 18% in this interval, that there is some choice of n that gives me 18% probability of being happy. And if I found that choice of n, say n is 100 worked, then that means that I have 18% of the numbers from 0 to 10 to the 100 are happy. And I can sort of do this again. And maybe I can iterate this and do it for as many times as I want. I can say something about the density of happy numbers as far out as I want. And I'm going to try to control the loss at each step. And so here's a tool I need to make this argument rigorous. I found this in, I guess it's Philippe Flagel. I don't know if I can say his name right. There's a book online called Analytic Combinatorics. It's a great book. And I found this theorem in it. And it's much stronger than the central limit theorem. So what it says is if I have n IID integer value random variables with probability generating function b of z, and each of the variables has mean, mu, variance, sigma squared. Now I have to assume that b of z is analytic and that it's aperiodic. I'll explain in a second what aperiodic means. But it says that this sum basically approaches a normal distribution. And it gives me the exact probability that this sum is a particular integer. And it gives me a nice error bound of O of n to the negative 1/2. Okay, if maybe this is a little bit confusing, this floor here. The floor is there because if you didn't have the floor and this was not an integer, well, the probability that an integer valued random variable is not an integer would be 0. So the floor is necessary. If the floor isn't there, it certainly wouldn't be true. And aperiodic means that basically the y sub I these random variables y sub I, the greatest common divisor of its support is 1. So for example, if y sub I is just 0 with probability 1/2 and 2 with probability 1/2, then you couldn't say anything of this type, because if y sub I is always even, then s sub n is always even. And so the probability that s sub n is an odd integer is 0. And so you couldn't hope to get something like this if you don't assume the aperiodicity. But in our case, if because 0 is mapped to 0, 1 is mapped to 1, I don't have to worry about that. So, okay, questions so far? And I define probability generating function. It's just the expected value of z to the random variable x. And so P sub k is the probability that your random variable is k. It's okay. And so I wanted to give a heuristic argument. Again, like, well, what I'm going to do is I'm going to use this peak at 10 to the 400, which has about 18%. I'm going to average over all possible choices of this random variable of like h of y sub n to say that at least some choice of n will hit happy numbers with high probability. And again, this is just, so far it's all heuristic, so I haven't said anything specific yet. But the biggest obstacle to making this rigorous is this O of n to the negative 1/2 term. And because specifically, I don't know the exact rate of convergence. I just know that it eventually goes to 0. And so for 10 to the 400, maybe the bell curve is hitting, if I expanded the interval from 10 to the 400 to 10 to the 401, maybe the bell curves in that interval still aren't very close to a normal distribution. I know it eventually becomes, but my point is that, yeah, the local limit law doesn't say anything yet. So I need some way to avoid this. Okay. And so here's a lemma that I'm going to use. Let I and j be intervals, and let S be a set of integers subset of I, and y a random variable taking integer values in j. And I want to find some shift of y such that y hits integers in S with high probability. So let me go to the board for a second. Okay. So I have j, and I have y is a random variable in j. And then I have I, which contains some set of integers S. So this is I. And in general, I'm going to assume that j is much smaller than I. And I want to find some shift of y that hits the integers, hit this set of integers in I with high probability. So, maybe shifting it to here works. And there should exist some shift. And to prove there exists some shift, I mean, just average over all possible choices of your shift. And how many choices are there? Well, let me shift it to this endpoint, and then shift. All shifts that make sense are basically from this endpoint to this endpoint. And the number of possible shifts to, I guess, cover this interval evenly would be, so it's size of I to shift from here to here. So that's size of I. And then I need to shift this last part all the way over here, and that'll be size of j minus 1. And so that's where this comes from. So does that make some sense that this argument should work? And prove is average over all appropriate choices of k. And just rewriting this in terms of density. If S has density D in I, then the probability that we can find, I'm just rewriting this in terms of the density. So if J is much less than I, this provides a nice bound, because this will be almost 1. But the problem is, a lot of times J will be too big. And so then I use a little bit more machinery. I use Chebyshev's inequality, which basically allows you to say that this random variable x is close to the mean. And so we can improve this previous lemma as in this form. So